Hello, welcome everyone. In today's class, we are essentially going to look at the analysis of an L-shaped beam that is subjected to vibrations. So this is a fairly interesting and also somewhat complicated example where we use what you have learned in vibrations and also what you have learned in terms of principal stresses and deflections and Castigliano's theorem and all those things, and we're going to put them all together. Okay? So essentially, we will look at the vibration of an L-shaped beam and determine the loading requirements in that beam to avoid failure. Again, this is a specific example, but the concepts that we are applying here can be used for other cases as well. Okay, so this is a fairly involved problem, so let's just go through the problem statement. Okay, so in this case, you essentially have an L-shaped beam that is subjected to a force P at the tip. Okay, so essentially you have a force P that is acting at the tip. Okay, we are given a few things. We are given that the members AB and BC lie in the XZ plane and the force P is applied in the Y direction. Okay, we are also given that both the members AB and BC have a circular cross section with a diameter of 50 millimeters, and we are also given the length of AB is 1.5 meters and the length of BC is 1 meter. Okay, and we are also given some of the material properties. The shear modulus is given to be 80 GPa and the Poisson's ratio is given to be 0.25. Okay, so the first part of the problem is somewhat simpler. Part A essentially asks you to use Castigliano's theorem to determine the deflection at C as a function of P and essentially use that to calculate the equivalent stiffness of the structure. Okay, and we are also asked to consider only bending and torsion. Okay, we ignore the effect of direct shear. Okay, so the first part is fairly simple. It's a question of just calculating the equivalent stiffness of the structure for the given loading configuration. Again, I want to emphasize that this K effective that we are going to find out is only true for a force in the Y direction applied at point C. So if you apply a force in the X direction at point C, the stiffness of the structure is going to be different. Or for that matter, if you apply a force in the Z direction, the stiffness is going to be different. Okay, so that's something that you must keep in mind. The second part is a little bit more complicated. Now it says that this P is not a constant force, but actually a time varying force, which is given by P naught cos 60T. Okay, we are also given that the equivalent mass or the effective mass of the structure is 3 kilograms and the damping ratio is 0.1. Okay, so these are essentially the parameters that you need to analyze the vibrations of the system. Okay, now what is being asked here is that you are asked to determine the maximum value of P naught. So P of T is P naught cos 60T. You are asked to find out what is the value of P naught such that the maximum principal stress at any point in the cross section at A, which is here, okay, that in that cross section, the maximum principal stress at any point should be less than 200 MPa. Okay, and you're also given another condition that the maximum deflection at point C should be less than 60 millimeters. Okay, so essentially you have to satisfy two different criteria, that the stress, the maximum principal stress at point A or the cross section at A should be less than 200 MPa, and at the same time the deflection at point C should be less than 60 millimeters. Okay, now it looks like there are too many things that are given here and there are too many concepts, so we'll try to go through this a little bit more carefully. So the first part is relatively simple, so we'll get through that quickly and then let's spend a little bit more time on part B. Okay, so part A is fairly similar. We have done examples like this before. So essentially, you are asked to find out what is the effective stiffness. So what we do is we essentially find out what is the total strain energy, and then we equate that to essentially half P times delta. Okay, to find out the strain energy, you essentially have to find out what is the moment and torque functions in segments BC and AB. Okay, so in this case, for segment BC, there is going to be only bending. Okay, so essentially you just have to worry about the bending moment function. For segment AB, you have to find out what the bending moment function is and also what the torque function is. Okay? For segment BC, it is actually very simple. We again use some kind of a local coordinate x bar, and we can say that mx, which is going to be the bending moment in segment BC, is nothing but p times x bar. Okay? In segment AB, the bending moment is going to be mz because it is oriented in a different direction, and that is going to be nothing but p times x bar. Okay? The segment AB also has a torque mx, which is actually nothing but p times 1, because for any point along the cross section here, here, the loading arm for p for creating a torque is just going to be 1 meters. So it's going to be just p times 1, which is nothing but p. Okay? But to be a little bit more specific, this torque is actually minus mx. The reason is because the torque is positive. We assume the torque to be positive when it is along the outward normal. Okay? And in this case, mx is along the inward normal, so the actual torque, to be precise, is minus mx. But it really doesn't matter, because if you calculate the strain energy due to the torque, you essentially have to square the torque. It's t squared dx over 2gj integrated over the entire length. So essentially, even if the sign is off, you're still going to get the same answer. Okay? But anyway, it's better to be a little bit more precise. Okay. So essentially, what you have done so far is find out what is the bending moment in the segment BC and the bending moment as well as the torsional moment or the torque in segment AB. Okay? Now, the question is just to find out what the total strain energy is. Okay? So the total strain energy is going to be UAB plus UBC, and essentially you find out what is the UAB and what is UBC. So this term is the bending in UAB. This thing is the torque in BC. This is the first term is the bending moment in BC. Okay, so bend in BC. This is torque in AB, and this is bending in AB. Okay, so actually I made a mistake that this is AB and that is BC. Okay, and the reason is because if you look at the limits of the integrals, so this is from 0 to 1.5, right? The segment AB has a length of 0 to of 1.5, so that is why it's 0 to 1.5. Whereas the segment BC is of length 1 meter, so that is why the integral is from 0 to 1. Okay, again, this is something that we have done multiple times, so it's not too difficult. Okay. Now, once you do that, you find out what the total strain energy is, and all you have to do is essentially take the derivative of u with respect to p, and if you do that and do the calculations, essentially you end up with an expression like this, and if you apply the limits, then you end up with an expression like this. Okay. So again, I have simplified some of the terms here. So effectively, your delta C, okay, which is the deflection at point C due to the force P, is given by 1.548 P divided by EI plus 1.5 P divided by GJ. Okay. So essentially, you can think of this as the deflection due to torsion, and this as the deflection due to bending. Okay. Okay. It is not quite one-to-one like that, but effectively you can think of that as bending and torsional deformation, because if you think of the bending term, it has a EI at the denominator. For the torsion, you have a GJ in the denominator. Okay. So the main thing that I want to point out here is that if you look at the expression for delta C, it is directly proportional to P. Okay. And there are no constant terms here. Okay. So what that means is that if you put P equal to 0, delta C is going to be equal to 0. Okay, which is obvious because if you don't have any force acting at the tip C, it should not have any deflection, right? And it is important because eventually when you calculate K effective, you have to get a number. Okay, it should not be dependent on P. Okay? But before we do that, we have to do a few things. If you look at this expression here, it has this EI and GJ terms. We are given the shear modulus and the Poisson's ratio, which means that we first have to calculate what the Young's modulus is. And that turns out to be 200 MPa or 200 GPa. And then you also have to calculate a few other things like the area moment of inertia I, and that has this value of 3.068 in 10 to the minus 7 meter to the 4. J is going to be nothing but 2I because this is a circular cross section, and that value turns out to be 6.136 into 10 to the minus 7 meters to the 4. Okay, so then essentially what you can do is you can take all these values that you calculated here and then put it into this expression. Okay, and if you do that, you essentially get an expression like this. Delta C is 5.432 times 10 to the minus 5 times P. Okay, this is what I was referring to. So the delta C expression is directly proportional to P, and it doesn't have any other terms. It doesn't have a P squared term, it doesn't have a constant term, it does not have any other term. Right? This is important because this tells you that the deflection at point C will be 0 if P equal to 0. And more importantly, if you now find out what K effective is nothing but P over delta C. Okay, now if you divide P divided by the delta C expression that we just found, you essentially are going to get a number. Okay? And that is important because the stiffness of the structure should be independent of P. Okay, the stiffness of the structure should just depend on its geometry, its boundary conditions, and the material properties. It should not depend on the force. If you end up with a K effective, that essentially depends on P, it means that you have made some calculation mistake or some conceptual mistake somewhere before in the problem. Okay, that is something that you must clearly keep in mind. Okay, so essentially what you have done is you have solved the first part of the problem. We have found out the effective stiffness of the structure for this particular loading configuration is 18,409.8 newtons per meter. Okay, now let's look at the second part of the question, which essentially asks you to evaluate the structure under a dynamic load where you have vibrations. Okay, so in this case, your P is some P naught cos 60t. Okay, so that is the force now. It is not just a constant force, but a time varying force. Okay. When you have to look at the vibrations of a system, the first thing pretty much you have to always know is what is its natural frequency. Okay, and that was the reason why we calculated this K effective. Okay, we are given that M effective is 3 kilograms. So if you put in the numbers, you effectively get a natural frequency of 78.33 radians per second. Okay, so the natural frequency is usually in radians per second. Okay, now if you look at this expression for P, it is P naught cos 60t. So essentially, which means that your omega bar, which is the forcing frequency, is 60 radians per second. Okay, that is what I have written here. Okay, so there is this natural frequency which is 78.33, and there is this forcing frequency which is 60 radians per second. So sometimes you use omega, sometimes you use omega bar. Okay, so it just to kind of acclimatize you to both these things, I have used omega here. Okay, now once you know what is this forcing frequency, your beta, which is the frequency ratio, is nothing but omega by omega n. Okay, and that is equal to 0.766. Okay, so just to be clear, sometimes the forcing frequency is given by omega bar, sometimes it's given by omega. It's just a variable, it's just a particular function that you use. Okay, but the frequency ratio is the ratio of the applied frequency, which in this case is 60 radians per second, divided by the natural frequency, which is 78.33. Okay, so that frequency ratio comes out to be 0.766. Okay, now thus far it's fairly straightforward. It's just doing some calculations. Now comes the kind of a more conceptual part. Okay, now when you have a time varying force like this, okay, then the actual force that is felt by the structure, or the actual force that is felt by the support, is actually quite a bit larger than the applied force. Okay, so here P is P naught cos 60t. So P naught is the amplitude of the force. But the amplitude of the force that is felt by the structure when it is vibrating could be quite a bit larger. And this is what we learned when we talked about force transmissibility. Okay, so even though the applied amplitude of the force is P naught, the actual amplitude that is felt by the vibrating structure could be quite a bit larger. Okay, so for that we have to use the force transmissibility equation to find out what the actual force that is being felt, or to be more precise, what is the maximum force that is being felt by the structure. Okay, and that is what we're going to do next. Okay, so we already calculated beta. Zeta is given to be 0.1. We know what omega n and other things are. So we can use this equation for F max, which is going to be P naught, which is the static or the amplitude of the static force, times this amplification factor, which is in the square root. Okay, now we know zeta, we know beta, we can actually put in the values and find out that the maximum force that is felt by the structure, or the maximum force that is conveyed to the support, is not P naught, it's actually 2.295 times P naught. Okay, so it's almost a factor of 2.3 larger. Okay, what does it actually mean? So here you have, let me just go back a little bit. So here you are applying this P naught cos 60t. Okay, but the maximum force that is being applied, or that is being felt by the structure, is actually 2.29 times P naught. So what does it actually mean for this problem? It means that the torque that is actually being applied at this cross section A is not going to be P naught times this 1 meter here. It is 2.29 times P naught times 1 meter. The maximum bending load, or the maximum bending moment that is being applied, is not going to be P naught times this 1.5 meters. It is P naught times 2.29 times 1.5 meters. Okay, so what essentially it means is that the effective moment, or the maximum moment felt at the cross section at A, and the maximum torque that is felt at the cross section at A, is now being amplified by a factor of nearly 2.3. Okay, so that is the effect of having a vibrational force. Okay, so effectively your T max, or the maximum torque at the cross section at A, is 2.295 P naught, and the maximum bending moment at the cross section at A is going to be 2.295 times P naught times 1.5. Okay, now once you know the maximum torque and the maximum bending moment at the cross section at A, you can essentially find out what is the maximum bending stress and what is the maximum shear stress in the cross section at A. Again, I want to emphasize that this tau max that I'm talking about is the maximum shear stress in the cross section at A. Okay, it is not tau max at the end at any plane. Okay, that we will get to in a minute. Okay, so effectively, if you look at the cross section at A, which is circular, you are going to have at some point, okay, we don't know which point it is, we don't have to really worry about it, you are going to have a sigma x that is given by this, and then you are going to have also a shear stress that is given by that. Okay, so those are the bending and shear stress, or the normal and shear stress, acting at the most stressed point at cross section A. Okay, so if you want to kind of be a little bit more clear, if you look at this cross section at A, you can think of some point in this cross section is going to have the maximum bending stress. Say let's say that point is here. If you draw a stress cube at that point, there is going to be a normal stress sigma x on that, which is given by this, and there is going to be some shear stress. Okay, it could be, let me use a different thing, so let's say some tau. Okay, and that tau is given by this. Okay, the main thing that I want to point out here is that it essentially means that the state of stress at this point is a 2D stress state. Okay, you have one normal stress and a shear stress. Okay, it's essentially a 2D stress state. When you have a 2D stress state, you can find out what the maximum principal stress is using this formula, which is sigma x by 2 plus square root of sigma x by 2 the whole square plus tau square. And where is this formula coming from? It is actually coming from from sigma P1, comma P2 is basically sigma x plus sigma y by 2 plus square root of sigma x minus sigma y by 2 the whole square plus tau square. Okay? So that is the expression for the first principle stress and the second principle stress for a 2D stress state. Here again we have a 2D stress state. Okay? And that's why we can apply this formula. And in this case, we also have sigma y to be equal to 0. Okay? So essentially you have only sigma x, and that is why you have the simplified expression. Okay. Now we have already found sigma x as a function of P naught, and we also know tau as a function of P naught. So essentially, you get the maximum principal stress as some constant times P naught. Now, if you go and recollect what the problem statement gave us, it basically said that the maximum principal stress at this cross section should be less than 200 MPa. So essentially, it means that this condition has to be satisfied, which means that P naught has to be less than 647.5 newtons. Okay? So this is the condition that has to be satisfied if for the maximum principal stress at this cross section A to be less than 200 MPa. But that is not the only condition that we are asked to satisfy. We are also asked to satisfy the condition that the deflection or the maximum deflection at point C should be less than its delta, that should be less than 60 millimeters. Okay? So this is a completely different condition. One condition talks about the stress at point A, the other condition talks about the deflection at point C. But we have to choose a P naught such that both these conditions are satisfied. Okay? And that is what we are going to do next. Okay? Now, because of this particular case, you have a single, essentially this is a single degree of freedom system, you know that the amplitude of vibration is given by this particular factor. So sometimes we use G to kind of indicate this. Okay? So which is given by P naught by K effective times 1 over 1 by square root of 1 minus beta square the whole square plus 2 zeta beta the whole square. If you want to think about it a little bit more carefully, this P naught over K effective essentially is the static deflection. Okay? What it means is that if this P was not a time varying force, if it was just a constant force P naught, that P naught by K effective would be the deflection that we'll get at point C. But because this P is a time varying force, which is given by P naught cos 60t, you are going to have an amplification of the displacement or amplification of the maximum displacement at point C, which is given by the second term, which is 1 by square root of 1 minus beta square the whole square plus 2 zeta beta the whole square. Okay? Now, if you look at this term, this P naught is something that we know. K effective we found out in the first part of the problem. We know what beta is, we know what zeta is, so essentially we can calculate what the second term is. And if you do the calculation, the amplitude of vibration at C is given by 1.215 times 10 to the minus 4 P naught. Okay? Now, the condition that we are asked to satisfy is that this particular amplitude of vibration at C should be less than 60 millimeters, which is what I have used here. Okay? And now, if you calculate what the value of P naught is, it turns out that P naught should be less than 493.83 newtons. Okay? Now, if you go back a little bit, we found out that if the stress, the maximum principal stress at the point A or the cross section at A has to be less than 200 MPa, the P naught has to be less than 647.5 newtons. Now we are finding out that if the deflection at point C has to be less than 60 millimeters, then P naught has to be less than 493.83 newtons. Okay? So essentially, if you want to satisfy both conditions, then P naught should be less than 493.83 newtons. Okay? So that essentially concludes the problem. So again, if you think about this problem, there are lots of moving parts, right? First, we have to find out what the effective stiffness of the structure is, right? Then we have to use force transmissibility to find out what is the actual force or the maximum force felt by the structure when it is getting oscillated. Okay? Then we have to use the concepts of 2D stress transformations and principal stresses to find out what is going to be the maximum principal stress at this point, right? Then we have to use the concept of Castigliano's theorem, or in some sense, you can think of it as energy methods, to find out what the deflection at point C is going to be. Okay, and the deflection depends not only on the static force but also the time varying component. That's why we have to use the solution for the forced vibration. Okay, and then we have to find out the P naught that satisfies both these conditions. And it turns out that P naught in this case turns out to be about 493 or 494 newtons. Okay, so again, this is a very kind of, I would say, an involved problem that uses a lot of concepts that you have learned in this class. So in some sense, that is going to be the last example we are going to look at in this class. Okay, with that, I will finish this lecture, and in the rest of the class or rest of the course, we will look at two new concepts, which is on stress concentrations and fatigue. Okay, thank you.